Hello everybody, happy Monday. By now you all should have taken the exam. I've finished grading all of the attempts. And in general the scores were pretty good. I think the median grade was around in the low 70s. Highest grade was like a 92. So there will be a curve. So in general, to get an idea for the curve, your grade on the exam will be one letter grade higher than your raw score suggests. So 80 and above will be an A, 70 and above will be a B, 60 and above will be a C, and so on. What I want to do for this week's lecture is just kind of walk through the exam, work through the questions so that if there are any concepts that you're still kind of unclear on, we can clarify those before we move into new material next week. So this week we're going to be working through the exam. Okay, so question number 1, it's asking what do we mean when we say that beta 1 hat is an unbiased estimator of beta hat. So it's just asking me what does unbiased mean. And most of you got this right. The answer is that the expected value of beta hat 1 is equal to beta 1. Basically, if we take many samples and calculate many beta hat 1s, then on average, the average beta hat 1 from all of those samples will be equal to beta 1, the population slope. Okay, it's also another way of saying this is the sampling distribution is centered at the population parameter. All right, number 2, also just kind of a definitional question. It's saying what does the equation y hat equals beta 0 hat plus beta 1 hat x? What does that mean if we're dealing with this regression equation here? And you should remember that when we put hats on our variables, we're basically calling them, or basically indicating that they are our sample statistics as opposed to our population parameters. So when you actually run a regression in Stata and get that number for the coefficient in the output, that's beta hat 1. It's our estimate. Beta 1 hat is the actual relationship between x and y that we're trying to estimate. Okay, so it's the sample regression function. All right, number 3, correlation coefficient. This is another just kind of definitional one. It doesn't lie between 0 and 1. It's not A because it actually lies between -1 and 1. It's a measure of linear association. That's just the correct answer. It has nothing to do with causality, right? We can think of lots of variables that have a high correlation coefficient but aren't causally related. If you watched the exam review video, we went to that website, Spurious Correlations, and saw a bunch. So it's not that one. And then the last answer choice takes on a high value if you have a strong nonlinear relationship. It's not that one. Remember, correlation coefficient is telling you about the linear relationship, not a nonlinear relationship. So the only one that makes sense is B. All right, next one. Ordinary least squares estimators. How do we get them? First one, connecting the yi corresponding to the lowest xi observation with the yi corresponding to the highest xi observation. I don't even know what in econometrics requires you to do that. It's definitely not A. B, making sure the standard error of the regression equals the standard error of the slope estimator. No, that has to do with the f-test. Minimizing the sum of absolute residuals. This is closer, but if you remember, the sum of absolute residuals, the issue with that is you have positive and negative residuals will cancel each other out when you add them together. So the sum of absolute residuals isn't a good measure of goodness of fit. So it has to be the last one, minimizing the sum of squared residuals. That's why it's called least squares. All right, next one. The sample regression line. Go through answer choices. 1 will always have a slope smaller than the intercept. No, there's no reason why the intercept will always be bigger than the slope. 2 is always the same as the population regression line. No, remember the expected value in our proof for unbiasedness. The expected value is the same, but any given sample, it's not going to be exactly the same as the population line. Cannot have a slope of 0. It's very easy to have a regression with a slope of 0. Oops, just erase this. It would just look something like this, where there's just no no relationship between x and y, so the fitted regression line would be flat. Okay, and then the last one is asking, we'll always run through the point x bar, y bar, and if you remember our equation for beta naught is equal to y bar minus beta 1 x bar. This is basically our regression line in point slope form if we rearrange it. And this is telling us that we place the intercept such that the line goes through the point x bar, y bar. So that's the correct answer to that one. It's D. The OLS line that we estimate will always go through the mean of our data. All right, next one, we're asking about the zero conditional mean assumption. All right, let's work bottom to top here. The estimated average value of beta naught is 0. No, that's not the zero conditional mean assumption. The expected value of the explained variable is 0, regardless of what the value of the explanatory variable is. We would write that out something like the expected value of y hat conditional on xi is equal to 0. And that's basically telling you that the covariance of yi and xi is equal to 0, which is basically saying there's no relationship between x and y, which, why are you running a regression? So it's not that one. The estimated average value of beta 1 is 0. This is actually the same as C. But when we're talking about the zero conditional mean assumption, remember we said that there are basically four different ways you can write it. The first is you can just say zero conditional mean. We can write it like this. The expected value of the population error term conditional on our explanatory variable is equal to 0. The other way we can write it is the covariance of the population error term and the explanatory variables is 0. And the last way we can say it verbally is that there's no omitted variable bias. Okay, so the answer to this one is A. The expected value of the error term is 0, regardless of what the value of the error term is. So that's basically another way of putting that one right there. Okay, so that's the zero conditional mean assumption. There'll be another question about that later on in the short answer portion. All right, number 7. This one is just asking what is beta naught, and this one you either know or you don't. It's the intercept. All right, D, I think pretty much everyone got that one. All right, number 8. This is asking us how do we calculate the sample slope. If you remember, our equation for the slope is beta 1 hat equals this summation over this summation, which we could rewrite as the covariance of x and y over the variance of x. Okay, so the answer to this one is C. A couple of people got tripped up and put B, but remember, looking at the denominator, this is the numerator from the formula for variance. So we want the covariance of x and y over the variance of x. So maybe some people remembered covariance over variance, but they forgot that it's the variance of x, not the variance of y. Okay, next one, OLS residuals are the sample counterpart of the population regression slope. Nope, that's beta 1 hat. Regression functions predicted values, that's y hat. Regression function intercept, that's beta naught hat. The only one that makes sense is errors. The residuals are the sample counterparts of the population errors. All right, this one, a low regression R squared. Remember, R squared is our coefficient of determination. All right, so does a low regression R squared mean the regression is bad? No. Most empirical econometrics papers don't even report the R squared because it's possible that there can be tons of other factors that influence y besides x, but x is still important. Okay, so a low R squared does not mean you have a bad regression. Similarly, it doesn't mean that there's no causal relationship between x and y. What it does mean is that there are other factors besides x that influence y. This last one, the sum of squared residuals, is low relative to the total sum of squares. This, I think, tripped up a ton of people, not a ton of people, sorry, like a few people. But if you remember our formula for r squared, it's equal to the explained sum of squares divided by the total sum of squares. Or, and we can also remember the identity that the explained sum of squares plus the residual sum of squares is equal to the total sum of squares. So if the r squared is small, it means that the explained sum of squares is small relative to the total sum of squares, or a small r squared means that this sum of squared residuals is big relative to the total sum of squares. So this is saying small, but it's actually the other way around. A low r squared means that the SSR is big relative to the SST. All right, confidence intervals. Allows you to make statements about the economic importance of your estimate. No, again, for that you need more than just the regression output. You need theory. Adds and subtracts 1.96 from the slope. This one is close to the truth. If you remember, I hate that I can't just erase these circles like normal. Sorry about that. Where were we? Sorry. Confidence intervals. All right, so if you remember, the confidence interval is going to equal your slope plus or minus some value t star times your standard error. And one very common value for t star, if your significance level is equal to 0.05, is 1.96. But remember, we're not just adding and subtracting 1.96, we're adding and subtracting 1.96 times the standard error. Okay, so it's not that one. Can be used to compare the value of the slope relative to that of the intercept. No. What we can do with a confidence interval is we can conduct a test about a hypothesized regression, population regression function slope. So remember, if you have your 95% confidence interval, it would tell you that, if our 95% confidence interval looked something like this, then, for example, we can't reject the hypothesis that beta 1 is equal to 0, that there's no relationship between x and y. We also can't reject the hypothesis that beta 1 is equal to 1, for that matter. But basically, if a value is within our confidence interval, then we can't reject it at the 5% level if we're doing a 95% confidence interval. All right, here we're getting into, we got our a example regression model. We're regressing wages on gender. All right, and it's telling us that we know that being male means that there's a lower probability of attending higher education. Okay, and which of these assumptions is not holding? So if you remember, we talked about omitted variable bias, where we've got education, and we've got wages. And what the question is telling us is that sex affects your education, and sex affects your wages. I should say gender. Okay, and so there's and then we're also interested in this. Okay, so there's a backdoor path going from education to wages. So we have omitted variable bias. Okay, and if you remember, we're violating our assumption of no emitted variable bias. Another word for assuming away emitted variable bias is the zero conditional mean assumption. All right, 13, probably the hardest question. So this is asking, what is the value of the slope parameter when it passes through the origin? Okay, so what does that mean? Well, let's start by writing out our equation for the slope. We know that beta hat 1 equals, again, this summation, oops, over this summation. Okay, and the question is telling us that the regression line goes through the origin. Okay, and so one way you can work through this is saying, well, one way that this regression line can go through the origin, that's telling us that the intercept is 0. Okay, and for the intercept to be 0, the point x bar, y bar is the origin, or 0, 0. So that's telling us that x bar is equal to 0 and y bar is equal to 0. Okay, so then if we plug in up here, we plug in that x bar is equal to 0 and y bar is equal to 0, we can get the special case of regression through the origin that the slope is going to be equal to that, which we can see is C. Okay. Emitted variable bias. When do we need to worry about emitted variable bias? Will always be present as long as the regression R squared is less than 1. That's not true. Your regression R squared will never be 1 unless y is a perfect linear function of x. Is always there but is negligible in almost all economic examples. That one's not true. We always need to be vigilant and worried about emitted variable bias. We should never neglect the possibility. 3 exists if the emitted variable is correlated with the included independent variable, but is not a determinant of the dependent variable. That one, it might help to think about that in terms of a directed acyclic graph. So what exactly are they saying? That's saying you've got some variable here, you've got some variable here, and you've got an emitted variable. And it's saying that it's correlated with the included independent variable. So you have that. But it's not a determinant of the dependent variable. So there's actually no backdoor path leading you from variable 1 to variable 2 by means of variable 3. So you don't actually need to condition on variable 3. All right. What we're worried about is when we have this, right? This is confounding. This is emitted variable bias. So we need it correlated with the independent variable and the dependent variable. It needs to be correlated with the independent variable and it needs to cause the dependent variable. All right, so best answer there is D. All right, here's a multiple regression question. We've got 2 independent variables, x1 and x2, and it's asking how do you interpret the slope coefficient on x1, beta 1. And it's basically saying, if you remember from the multiple regression slides, beta 1 is measuring the effect of x1 on y holding x2 constant. Another way of saying holding x2 constant is ceteris paribus, so the answer to that one is C. All right, number 16, we're saying x and y are positively correlated, so what's the value of the slope going to be? This one's pretty easy. It's going to be greater than 0. All right, next one. This one, you're going to use your, if you remember, our emitted variable bias formula, our OVB formula. which tells us that this is the slope in the short regression. Okay, basically when we fail to control for the omitted variable, is going to be equal to that. This is the slope in the long regression plus this is the effect of omitted on dependent. And then we also have this, I think we used gamma. All right, that just means this is the effect of omitted on included. It's the relationship between our omitted variable and our included variable. Okay, so it's asking, the bias is positive, so this is our bias term here. We're asking, when is this going to be positive? Well, we need this term, beta 2, to be positive, and this term, gamma 1 hat, to be positive. Okay, so we need there to be a positive relationship between our omitted variable and our dependent variable, and we need there to be a positive relationship between our omitted variable and our included variable. So going through these, beta 2 is greater than 1, and x1 and x2 are positively correlated. That's telling us what we need to know. So this is greater than 1, and this is greater than 1. And that's how we know that the bias term is positive, and our slope coefficient in the short regression is an overestimate of the true effect. All right, this is again just kind of a know it or you don't question about the slope, or sorry, the intercept, and you should know the formula for the intercept is y bar minus beta hat 1 x bar. Pretty simple. That's again just telling you that our regression line, our line of best fit, is always going to go through the mean of the data. Okay, number 19, almost done with a multiple choice. This one is just an identity. You should know that the total sum of squares is equal to the explained sum of squares plus the residual sum of squares. And this is telling us that the explained sum of squares is 35. And the total sum of squares is 49. And so you can just use algebra, subtract 35 from 49, you get 14. All right, and number 20, this is giving us 4 95% confidence intervals and asking us to say which of the following is the most convincing evidence that a policy intervention was indeed effective. Okay, so let's ask ourselves, what would it mean? How could we tell if a policy intervention wasn't effective? And it's probably not effective if it's possible that there's no effect, that the relationship between x and y is 0. Okay, so remember, a 0 coefficient means no relationship between x and y. No relationship between x and y is at least reason to suspect that a policy isn't effective. So if 0 is in our 95% confidence interval, we can't really be convinced that our policy is effective. Okay, so first one, we've got a negative on the left and a positive on the right, so 0 is within that one, so can rule out that one. Same here, same here. The only one that doesn't include 0 is C. Okay. Numbers 21 through 24 are all kind of 4 parts of the same question, and these all came from material in the selection bias video. Okay, because if you remember, we wrote out this really long expression that expected value of yi conditional on di equals 1 minus expected value of yi conditional on di equals 0 is equal to, deep breath, expected value of yi1 conditional on di equals 1 minus expected value of yi0 conditional on di equals 0 plus, can I click and drag? Okay, I guess we'll just kind of, oh, I can click and drag. Plus the expected value of yi0 conditional on di, oh sorry, this should be di equals 1. Okay, conditional on di equals, order doesn't, how did I do it in there? I did 1 and 0. Conditional on di equals 1 minus the expected value of y0i conditional on di equals 0. Okay, so we got this whole term. All right. And we're talking about this in the context of pregnant women drinking coffee. Okay. And, you know, we saw that in observational studies, so let's define our terms. Okay. So yi is the observed rate of complications. Okay, di is caffeine intake in just binary terms. Okay, but we've also got, if you remember, that and that. These are called potential outcomes. Okay, so y1i is the potential rate of complications if a person consumed caffeine. And this is the potential rate of complications if a person abstained. Okay, so the first question is asking us about this term here. All right, and remember, this is saying we're just subtracting the observed complications of people who drank caffeine minus the observed complications of people who didn't drink caffeine. Another word for this is the simple difference in means. And the question tells us that in observational studies, complications are higher among people who drink caffeine. So we know that this is positive. All right, so that's question 1. You need to say this is the simple difference in means and it's positive. Remember, it's a couple of people said it's a causal effect. Remember, this is just what we're observing. The whole point of this equation is to tell us that this is not necessarily equal to a causal effect. Okay, so for the next one, we're moving on to this green term. Okay, this is the outcomes, the rate of complications for people who drank caffeine, minus what their complications would have been if they didn't drink coffee. In other words, this is a real causal effect, right? We're subtracting one potential outcome from another, and this is the average treatment effect on the treated. Okay, this is the causal effect. This is what we're really after if we're looking to give pregnant women advice on whether or not they should drink caffeine. Okay, and which of these do we know? Well, this is the potential rate of complications if people consumed caffeine for the people who actually did consume caffeine. So we know that. This term here is actually the same thing as this term here. All right, we just rewrote it in potential outcome notation. So we know this. This term, on the other hand, is a counterfactual, right? It's we'd have to look into another universe where all the people who drank caffeine didn't, and then observe what their rate of complications would be. So this term right here is a counterfactual. We don't know it. Okay, so to get credit for this one, you would have to say the green term is the average treatment effect of the treated, and we know this term is a counterfactual. Okay, the next term has us looking at this one, and this, if you remember, we had a name for it. This represents selection bias, our arch nemesis. Okay, and notice that this term here and this term here are the same. So this is just the same counterfactual from before. Okay, so you would, and this one, let's see, get another color. This term here is actually equal to this term here. Okay, so this term we know, it's just the observed rate of complications for people who abstained. And then this term here is the one we don't know. It's the potential rate of complications of the people who did consume caffeine in an alternate universe where they didn't consume caffeine. Okay, so that's your answer to the third one. Okay, now we're going to get into Emily Oster's point, okay, and what she notes in her book, Expecting Better, and she did a podcast with Russ Roberts where she talks about it. If you're interested in more, I look it up, just search ECON Talk, Emily Oster, O-S-T-E-R. And what she points out is that women who feel more nauseous during pregnancy are less likely to have complications. So if a woman is feeling very sick, she's throwing up a lot, that is actually a good sign for the pregnancy. Okay, and what that means is the women who don't feel sick are more likely to have complications, and the women who don't feel sick are more likely to drink coffee, right? If you're throwing up all the time, you're probably not going to drink as much coffee. And so what she's pointing out is this bias term is likely positive, okay? This term, or sorry, it's negative. It's negative. Wait, sorry, it is positive. Okay, because this term, the rate of complications among the people who drank coffee, had they not drinking coffee, is actually lower than the observed rate of complications for people who didn't drink coffee. The counterfactual is actually lower than the observed. Okay, and that's going to bias our whole expression, this whole thing here. That's going to bias it upwards, which means that this is an overestimate. And in plain English, he's basically saying caffeine might not be as dangerous as we think because of this selection problem. Okay, so basically all Oster is saying is the selection bias term is positive, meaning that the simple difference in means is an overestimate of the true effect. All right, so that's those questions. If you're still unclear, I would go back and watch the selection bias video. All right, number 25. I think this is the question that most people missed. And it's from the most recent lecture before the exam, which was on multiple regression. And basically what you're doing in this question is you're running two regressions. The first thing you're doing is you're regressing X on Z and getting some residuals, and then you're regressing those you're regressing Y on those residuals. And I was asking how would you interpret beta hat 1? And a bunch of people said, you know, oh, it's the expected increase in yi from a 1 unit increase in epsilon squiggly I, the residuals. And that's technically true, but in order to get full credit, you had to know that this is our, this is how we obtain the slope for a multiple regression model. So we've got xi, zi, and yi. And if you go back to that lecture on multiple regression, what you learn is that if we were to estimate this model, then this coefficient from this bivariate regression would be the same as this coefficient in our multiple regression model. Okay, when we run this side regression like this and get this residual and then regress our dependent variable on the residual, what this slope is telling us is it's the effect of xi on y after controlling for z. All right, so that's how you got full credit and a correct answer, is if you said that you could either write out this model and say that it's this slope coefficient here, or you can just say it's the effect of x on y after controlling for z. Okay, so I think only like 2 people got that. So go back and watch the multiple regression video. All right, 26, I think almost everybody got this right. It's pointing out issues that can lead to faulty conclusions being drawn from randomized controlled trials. And if you watch the randomized controlled trials video, we talked about things like non-random attrition, people leaving the experiment in different rates based on their treatment status. We talked about substitution bias, how maybe people can seek substitutes for treatment outside of the scope of the experiment, which would bias your treatment effects towards 0. We talked about things like scale effects, maybe something that works really well in an experimental setting doesn't scale well when you blow it up to like a national or state standard. Hawthorne effects, people acting differently because they're being observed. Any 3 of those issues would get you full credit, and I think most people got them. 27, when proving the unbiasedness of OLS, we assume that the covariance of the error term and our independent variable is 0. What exactly are we assuming about our data? A lot of people just said we're assuming that the covariance of the error term and x is 0, which is just kind of self-explanatory. What I was really looking for, what would give you full credit, is if you understood that this was the 0 conditional mean assumption. Saying that this is the 0 conditional mean assumption got you like 4 points. To get 5 points, you had to say what exactly the 0 conditional mean assumption meant. And what it means is that there are no omitted variables. Basically, we're not leaving out anything that is correlated with both x and is a determinant of y. We're assuming that x is exogenous. Okay, so that's what you had to do is to get full credit is to know that the 0 conditional mean assumption is about assuming away omitted variable bias. All right, and the last question, this was kind of a computational one, and this just required you to know your formulas. And the 2 formulas you need to know for this question are our slope formula, which is the covariance of x and y, x and y over the variance of x, and that our estimated intercept is the average value of y minus our slope coefficient times the average value of x, okay? And so a good place to start is our slope. We need the covariance of x and y, right there, negative 300. We need the variance of x. Our x variable is student-teacher ratio, so 25. Okay, and then if you just use a calculator. Or sorry, why did I say 25? It's 6. That's the mean. Right, remember we want the variance of x. Variance of ratio is 6. I was wondering why the math was not working out to the answer I knew. All right, so you divide negative 300 by 6 and you get negative 50. So that's beta 1. All right, next we can plug that down in here. We need the average value of y, so that's the average SAT, 1000. Minus negative 50 plus the average value of ratio, which is 25. Okay, simplify this, 1000 plus 50 times 25. All right, 50 times 25 is 1250 plus, oops. So we've got 1000 plus 1250, or 2250, is equal to beta naught. So now we can write out our expression for the regression line. You can say that SAT sub I is equal to 2250 minus 50 times ratio I. All right, and now all we have to do is plug in. We want the predicted SAT score of a school with a student-teacher ratio of 20. So we'll just do negative 50 times 20. So that's just the predicted value. Okay, so 50 times 20 is 1,000. So 2250 minus 1,000 gives you 1250. And that's the answer. Okay, so you had to know your slope formula, your intercept formula, and then just set up the equation, plug in 20, and you get 1250. All right, and that is all the questions. Okay, so if you still have questions about the exam, any problems you're still unclear on that you might want me to work through, let me know in this week's discussion board. If there are questions that you got wrong or material that you still are unclear about, go back and watch that week's video, and also let me know. And this Friday, I will, anything that you're still unclear about up to the midterm, I will try and explain it again. I'll try coming up with new examples. So this week is just your opportunity to get everyone kind of on the same page before we start moving into new material. But yeah, in general, good job on the exam, and I will talk to you guys on Friday.